Okay, this is number 41 in chapter 22. So this is a total internal reflection problem, but it involves sound. The other problems we've looked at has involved light. Now there's a key difference between sound and light, and this totally threw me at first. The difference between sound and light, if you have, so let's draw a boundary. So here we have, let's say, air on this side and water on this side. So water is more dense than air. So if you have a ray of light that travels from air into water, where is the light going to be traveling faster? Is the light going to be faster in air, or is it going to be faster in water? It's faster in air. So air is where light travels faster, and water is where light travels slower. Now, whenever a wave travels from a medium where it's going faster into a medium where it's going slower, the refraction is going to be towards the normal line. So that dotted down the middle is the normal line. The refraction is going to be this way. And here's a good analogy. Okay, this analogy right here. So if you have this toy car that's rolling like on a hardwood floor, it's cruising in, it's on a hardwood floor, and then it reaches carpet. So you can kind of imagine what's going to occur. So with this wheel right here is going to hit the carpet first. So what does that do to the toy car? It's going to shift the motion that way, which is closer to the normal line. So the toy car is going faster to slower. The change of direction is towards the normal line. Now, if you're looking at sound, so over here this was for light. Okay. So if you're looking at sound, if you have air and water, well, it's the reverse. For sound, sound travels faster in water than it does in air. So it's going to be slower. So if you have a sound wave, which we can indicate with an arrow, so if you have a sound wave that's coming from air, let's say, to water, which way is the refraction going to be now? So it's basically the reverse. So instead of going from fast medium to slow medium, it's like this toy car is going the other way. Which way is the refraction going to be? Away from the normal. So the big thing here, the big thing to realize is it's really all about where is the wave traveling faster. Whenever you're going from faster to slower, the refraction is going to be like this. It's going to be towards the normal line. Whenever you're going from slower to faster, the refraction is going to be away. Okay? So that's the one big thing in this problem is that we're now dealing with sound instead of light. All right, so let's set the problem up. So we have a sound wave traveling in air, and it's going to meet a concrete wall. So let's get this to black. So let's say right here is a concrete wall, and here comes the sound wave. Comes in like this. So this side is the air, this side is the concrete. Okay, so some of this is going to reflect off like that, and then here's the normal line. And we're going to call this theta 1, and then we'll call, this will be theta 1 also. Angle of incidence always equals angle of reflection. Now, which way is the refraction going to be? So for a sound wave, so where does sound travel faster? Sound travels faster in concrete, and then in air it travels slower. So as we just said, if you have a wave that's traveling from slower to faster, when it enters the new medium, which way is the refraction going to be? It'll be away from the normal, which is the opposite of what happens with light. If light goes from air into a denser medium, the refraction is going to be towards the normal. Okay, so what I'm going to do here is, this is a total internal reflection problem. What they're asking us to find is the critical angle. Find the critical angle for total internal reflection. So where does the critical angle, or when does the critical angle occur? It occurs when the refracted ray is at an angle of 90. So the refracted ray is boom like this, we're going to say theta 2 equals 90 degrees. And then therefore theta 1 is the critical angle. So now I'm going to write out Snell's law. So Snell's law is N1 sine theta 1 equals N2 sine theta 2. But what we just said is that theta 1 is the critical angle when theta 2 is 90. And then what is sine of 90? 1. Okay, so now we've reduced it to this. We have N1 sine of the critical angle is equal to N2. Is there any mention of the index of refraction in this problem? None. So here's what you can do. So the definition for index of refraction is C over V. Is the speed of light going to be relevant to this problem? No. But watch, you can do this. Take this, plug it in for index of refraction right here. So instead of N1, we're going to have C over V1 multiplied by sine of the critical angle is equal to C over V2. And then what drops out? C. Then C cancels out. So sine of the critical angle is going to be equal to V1 over V2. So V1 is the velocity in this medium, which is 343. V2 is the velocity in this medium, which is 1,850. So we just plug in. So this would be 343. And then V2 is 1,850. So the critical angle comes out as 10.7 degrees. Yo. Oh, sure. Sorry.